it's Cliff here. In this video I'm going to go into the setup and use of a passive touch probe. In this video series probing around, so far I've done a video on Heimer versus a probe, and where we go into the speed and ease of use of a touch probe, and also I touch on the accuracy of a touch probe if you're interested in that subject. And I've done a video on impact tolerance of these impact tolerant touch probes. In this video I'm going to go into setup and use. It applies to the Hallmark ITTP, but a lot of it is the same as the Tormach probe. I think it's the SPU40. I hope to do videos in the future on a couple of other subjects relating to the probe where I want to go more deeply into accuracy, and also want to do another video on long-term reliability and serviceability of these probes. The Hallmark probe's been out for over 2 years. It was February in 2017 that it was launched, so it's been in service for 2 years and still no significant problems. Alright, I'll get on with it. Cheers. So when you first receive your probe, if it's a Hallmark ITTP, the first thing you do is take the end cap off and put some of the electrical fluid gel into the 3 little reservoirs where the contacts are, and that means that the electrical contacts are submerged in this gel, and that gives the contacts a much longer term of reliability. You get less oxidization and you get lubrication of the contacts, which gives you more accuracy and a better long-term reliability. So when you've put the end cap back on again, there's no way that the stylus tip can be perfectly concentric, and so when I package up these probes I don't even dial it in concentric in the first place, because there's no point, because by the time you've installed the electrical fluid in the reservoirs and screwed the end cap back on, it'll be at least a little bit out, so you might as well dial it in from it being a long way out. So all these probes, when they're received by the new owner, need to be dialed in concentric. Okay, so let's talk briefly about dialing in the tip of your probe concentric. Obviously the center line of the spindle needs to be represented by a concentric tip. It's no good if you have run out there. So when your dial indicator, a light finger indicator, is in contact on the end of the stylus tip, you need the probe, when it's rotated, to show that it's concentric, that the stylus tip is in the center line of the spindle. So I've had a few questions from people asking about how to do this, and I go into it in the operator's manual video that comes with the probe, but I just wanted to explain it a little bit more thoroughly in this video. So let's just talk about the mechanism of how it works. I spent quite a bit of time developing this design a few years ago when I was developing the probe, because ease of adjustment and staying in adjustment is really important. And I put a bit of time into developing a system of adjustment that's very quick and easy. So basically how it works is that the arbor has a flat face cylindrically ground flange, and the body is pulled up against that flat face cylindrically ground flange with a brass nut and a special spring washer. You know, I couldn't source the right spring washer from anywhere in the world, and so I ended up that I now machine and make those washers in-house. So that provides just the right amount of tension. In a minute I'll show you a little clip of the amount of adjustment there is there, and you can see graphically how it works. Okay, well, there's 3 adjusting screws, and I've backed those right off so that I can show you with this dial indicator registering the movement how much adjustment there is with the body pre-tensioned to that shank. Let's have a look here. Hopefully you can see there's a big amount of adjustment, and it's pulled up against the flange of the shank. And so all we need to do, and it's pre-tensioned by that nut and that special spring washer, so all we need to do is to back off and tighten those 3 adjusting screws to get concentricity. Okay, let's go through actually setting the probe concentric. So we've got a light finger indicator touching the stylus tip, and when we rotate it we can see that it's not concentric. So it's really helpful if you're procedural about this and that you really understand what you're doing, otherwise you can be chasing your tail around in circles for ages. So have a look at your dial indicator, work out which way the stylus of the indicator moves, which way the needle moves, and what the effect is of tightening these set screws. And so when you've worked it out, in my case, if I rotate the probe and the needle of the indicator goes anti-clockwise, that's that way, then the set screw to the front needs to be tightened. That's that way. So back off all the set screws, rotate it to its most anti-clockwise position, tighten it, back off that set screw, rotate it again. The most anti-clockwise position is there, tighten it, back it off again. And you can see very quickly you can dial it in. This is probably going to make a liar out of me and take half an hour, but the principle is you have a strict procedure. Okay, now with about 3 adjustments we've got it within, what's that? Within about 100th. So what we would do now, we've passed the stage of backing off and tightening and shunting the probe into place. Now we want to snug up the screws. So go to its most anti-clockwise position, which is there, snug up the screw, leave it snugged up, just give it a slight little bit there. Again, you can see there, I'm almost spot on now. There you go, that's pretty right. So you snug up the 3 screws and you've got your needle dead steady. You've now got the stylus tip adjusted, and it should only take a few seconds. Perhaps the first time it'll take you a few minutes while you establish the method and the procedure. So to keep you on course with that adjustment procedure, it's a good idea to have a little note. For example, if the dial indicator needle goes anti-clockwise, then you need to tighten the front set screws, and that way you're not working against yourself. Once you've set the stylus tip concentric, now it's a good time to set in the tool table the stylus tip diameter. And if you measure the stylus tip diameter carefully with a micrometer, you would think you'd just put that into the tool table so the software can do the maths and work out the radius and where the center line is. But it's not quite that simple. We have 2 factors called pre-travel and pre-travel variation that need to be factored in, that need to be understood. I'll just talk about it very briefly here because it's a big subject. So on the tool table, and with Pathpilot it's tool number 99, you set the probe diameter here. But it's not the actual diameter, it should be the effective diameter. And the effective diameter is the actual diameter less 2 times the pre-travel, the average pre-travel, because it's a diameter. If it was a radius, it would be less one of the average pre-travel. Now what is the pre-travel? Well, pre-travel is the name given to the amount of movement that the stylus, the distance the stylus moves from contact to electrical trip. Now in these impact tolerant touch probes, they have a very stiff stylus, and the average pre-travel is very low, much lower than other low-cost touch probes, but it is still a very small amount. It is about 1.2 thou, or 1 thou and 2/10 radius, or 2.4 thou on the diameter. So whatever diameter your tip is, if it's 5/32, you measure it with a micrometer and you subtract 2.4 thou on the diameter, 2 thou and 4/10, and you will get a pretty accurate average pre-travel to enter in. and you may be, if you're in metric, you'll be doing that in metric. If you're in inches, you'll be doing that in inches. So what is pre-travel and pre-travel variation and average pre-travel? Well, it's a big subject, and for those of you who are interested, if you look back on my YouTube channel Thread Express, I did a series. If you click on playlists, back in 2015 there's a playlist called Touch Probe 2015 R&D. There's several videos there documenting my journey of discovery, learning about pre-travel and pre-travel variation. But if you just watch the first few videos, a few minutes each, you'll get a pretty good understanding of what it is. I won't cover it deeply in this video. I think I should do another video in this series called Probing Around, and call it Accuracy, and then I'll go into pre-travel and pre-travel variation more deeply. Okay, so once we've set the probe concentric and entered the diameter in the tool table, we're now ready to plug the probe in to the accessory socket, a 5-pin DIN plug, and think of some way to tidy up your lead or your cable so it's not draping in the cutting oil or chips. And you might want to have a little block for your probe that carries the probe in its as-use orientation, that's in that orientation, so that the gel stays in the little reservoirs. So your probe is stored in a little block. It might be off the machine, it might be in your mechanic's cabinet, it might be clipped onto the front of your enclosure, or it might be screwed up on the side of the cabinet door. Just make sure it's in an area that doesn't get sprayed with chips and coolant. Now I know some users leave their probe plugged in, and if you speak with Tormach about it, they will say that's not best practice. I know some people are getting away with it, but it's not best practice, and let me try and explain why. Okay, so we've got the probe plugged in. Let's have a look inside the electrical cabinet. Look at the main control board. You can see a little green LED there. That's showing that the probe is plugged in, and there's a little optical isolator in there. Now what happens is, when the probe's plugged in, the circuit is live. There is electricity flowing through the probe, and if I trip the probe, here I'm just moving the probe mechanically, you can see the little LED going on and off. So when the probe is plugged in, that circuit is live. When the probe is tripped, it sends a signal through to the opti-isolator, and that trips the software. Now if you leave the probe plugged in, there's electricity flowing through that circuit all the time, and there's some debate as to whether that's a good idea or not. Some of you electronics experts might like to comment on this. Is it going to cause that circuit to degrade more quickly, the opti-isolator, or not? It's probably best practice to have it disconnected and not to have current running through the circuit. When it's running through the circuit, it's also running through the probe, and that may cause the contacts in the probe to not last as long. That may cause electrically generated corrosion or arcing, and I'm not sure how big a factor it is or how big a problem it is, but best practice is to have the probe unplugged. Most of you will know that the probe accessory socket is located there on the traditional Tormach machines, but on the new generation M and MX machines, it's been moved from that position around to the end of the electrical cabinet, probably for CE compliance purposes, and it's not quite so convenient. You can't just reach across and plug it in as you used to be able to, so you might want to relocate or position that DIN plug somewhere on the front of the machine. You might have a block for your probe on the outside of the enclosure so it doesn't get sprayed with coolant and chips, and you might want to have a plug somewhere near. You could pick up that component from your electrical supplies shop and hardwire it in, or you could just use temporarily an extension lead din to din. You can pick them up on eBay or Amazon for a few dollars, or even Tormach, and just plug it in and have it hanging loose here somewhere so that you can conveniently plug your probe straight in and plug it in without having to thread it through to that back side socket. Okay, so you've plugged your probe in. Now go to the settings page and check that you have it set to passive probe. Tick that little button and set tool number 99 here, and set a feed rate of around 1000 millimeters a minute. You might as well run the probe quite quickly, or 40 inches a minute if you're in inches. You think, oh well, if I run it slower it'll be more accurate, but don't forget the probe routines have a rapid routine to get it approximately in position, and then a very slow final touch off to get precision. So even when you set it fast, you're still getting a slow precision final probe on the key probing movements. So once you've set those three things, passive probe, tool 99 and your feed rate, you can test. Let's switch it now to the probe page. Okay, so we're going to do a quick check now. So if you put your finger on the stylus tip so that you can move the stylus and have a look at the accessory input indicator, you can see when you move the stylus tip, the indicator light comes on. That's registering that everything's working, and you can check it in every direction and make sure that it comes on and off. Let's just go through that again. So when the probe contacts the work, it's deflected and it breaks the circuit. So when the probe trips, the accessory input indicator comes on green. Normal state is off, tripped is on green. And on the other page, if we go to status, normal state is off, accessory input off, tripped, it goes green. Please note I am working on Pathpilot version v2.1.4. It may be a little different on other versions. Okay, now we're ready to set the Z height. I won't spend a lot of time on this because it's well explained in the probe page, probe ETS setup. So first of all, disregard the ETS setup. That's the electronic tool setter. You're just interested in these two sections. Step 1, remove the tool and R8 collet from the spindle. Enter 0 in the tool DRO. Jog the spindle down with a feeler gauge, position between the spindle and reference surface. So the bottom of the spindle can come down, for example, onto a 1, 2, 3 block, and when you're lifting it up, if you push it in, it'll slip underneath until it, and just adjust it with a very fine steps so it's just dragging underneath the bottom of the spindle nose. Check that either the collet's out or you're not in that far so the collet's not interfering. So you're setting the top of the block to a snug fit with the end of the spindle nose that the TTS flange pulls up on. If you're using a feeler gauge as suggested here, then you need to have that feeler gauge, the same feeler gauge for the second stage. So that's the first stage. When it's in that position, you set the reference height and then that loads into the software. The second stage is you lift the probe up and you touch it off on that block with or without the feeler gauge, depending on whether you're using one. So let's just go through that. Step 2, place probe in the spindle, enter 99 in the tool DRO. Make sure the probe polarity, active or passive, is set correctly. Click the button below. So the probe will now move and set the probe length. And if you look in the tool table, where are we? Offsets, you'll have that number there, tool length, loaded in automatically for you by going through that two-step procedure explained here clearly in the probe setup. So okay, so you've loaded that length in there, and I know from emails from users of the Hallmark probe and other probes that sometimes they get a slightly different depth in their machine part than then would be ideal. It may be a thou or two different. And the reason for this, there's multiple reasons. It could be because there's backlash in the head, that there's stiction and racking of the head. It could be because the thermal expansion. It could be that the slight collapse of the TTS according to how tightly the drawbar is pulled up. It could be the way you set the probe in the first place. It could be the way that your tool is measured off the machine with your measurement method, whichever way you do it. So the end result is that you find that instead of machining a pocket of 10 millimeters deep, it's 1 or 2 thou deeper or shallower. Now the easiest way to get around this, rather than trying to work out what is the cause of this discrepancy, is just to change the length in your probe offsets page. If you change this length slightly by that amount, by that 1 or 2 thou, then you can continue with the method you've been using to measure all of your tools. You don't have to change each of the different tools, because you can just continue with that method and just change the relative distance for the tool number 99, the probe length. So make an adjustment there, longer or shorter, to compensate for whatever the error is. You may not be able to find out what it is. It may be something as simple as backlash. Okay, so once you've finished setting up your probe, you can move away from this page and have a look, if you're using Pathpilot, at the probe page XYZ probe and rectangular circular page, and have a look at some of the probing routines that you have. I don't want to spend too long on this, I want to keep the video fairly brief, but for 2D probing of a corner, you can change the corner that you want to probe and find the work origin, set the center line of the spindle to any of those corners. The same for an internal corner. And then you can also manually set up a simple routine where you probe X plus, X minus, Y plus, Y minus, find that dimension, or set the work origin, the spindle center line. You can also set the Z and set the work origin, or find the Z. And then on this page, rectangular circular, you can find the middle of a bore or square pocket, the middle of a gap in the X or the Y. You can go around the block and find the center of a block or a circle, and you can also use it to set work on the A axis. I've had a couple of questions for people asking, well, how do I know where to put the probe when I want to conduct a routine? Well, this little red circle is where the probe approximately needs to be jogged to. It's not critical, but approximately in that position. So wherever the little red circle is shows the relative position to the work. I'll just do a couple of probing routines now to show you that. So say we want to set our work to the center line of the spindle on the back corner. That's that surface and that surface. So we jog the probe to approximately that position as shown in the graphics on the probe page. Change the corner to that position, then just click on the button. See, it makes 2 moves. And for the Z, you can either probe Z, set work origin, or find the Z. So let's go probe Z, set work origin. So we're all set up to the top surface of our block. Alright, thanks for watching. Catch you next time.